All right, so today we are going to start on lists and list-based data structures. Previously, I had announced that we were probably going to do like multi-tier architecture or something here as a transition to the second half. I decided against it. It's really more of just a one-off anyway, and I actually wanted to code today, so we're going to do this tutorial style. I'll give you a motivation for what we're going to do. It's something that you've been using in Java up to this point anyway, and we're going to learn how it's actually done under the hood. But we're going to start implementing lists and eventually list-based data structures. So remember that we are online. If you have any questions, go ahead and post to Piazza or to the YouTube live stream here. But otherwise, so our motivation here is that we want to have what are called dynamic data structures. And we've introduced this before with lists, sets, and maps, right? All of those are going to be better than arrays. And hopefully you're using them in Java now that you have access to them. If you're in a programming language like, say, C that doesn't have easy access to this kind of stuff, doesn't have it built into the language necessarily, then you find that it is way easier to use lists, sets, and maps, these dynamic data structures. And what we're going to be doing throughout this process is we're going to be leveraging everything that we've covered up to this point as far as object-oriented programming goes. We're going to follow good encapsulation, good abstraction, and good polymorphism, and maybe even inheritance here, so that we can design these data structures. Okay? So let's take a look at a world without lists, right? A world without lists means that you are going to have to be using a regular old array, okay? What are the what are the disadvantages here? Right. Say what? I can't hear you. Memory allocation, right? If I want to create an array of size 10, right? Then each, by the way, an integer takes how many bytes? 4 bytes. So this is allocating 40 bytes somewhere on the heap or something like that. But once that 40 bytes is allocated, can it grow? Can it shrink? No. And what if I was only going to use, like, say, 5 numbers, right? I didn't know up front because I wasn't going to, I don't know how many numbers I actually need. I just said, oh, 10, that's maybe an overestimate or something. You only end up needing 4 or maybe 3 or 9, right? Or maybe you underestimated and you said, well, actually, when this program runs, I actually need 50 integers, right? So there are lots of problems with using a regular old array, right? That once arrays are bad, all right? And I'll put that into quotes there because it's not a value judgment or anything. It's just that they're not as useful as dynamic data structures. Once created, the size is essentially fixed. Now, in a programming language like C, you can call realloc, and you can shrink and try to shrink and grow it. This is a companion to malloc, if you remember malloc. But it's not guaranteed to work. Because if you have 40 bytes here and you want, say, 4 more bytes for 1 more integer, but that memory right there is being used, right? Then it's going to error out, and you're not going to be able to do it, right? Once created, the size is essentially fixed. We have to do a lot of bookkeeping. Even in Java, we have to do some bookkeeping to keep track of which indices have been used and which are free. So if you create an array of size 10 and you only put 3 things in it, right? Well, then you have to keep track of these other 8 things that are unused and that you can still, use those. If you put in 10 values here and then you end up deleting a few of them, right? Now you have gaps, right? Deleting or removing elements may leave gaps, right? And you don't want that. You want a contiguous allocation. You want to treat things from 0 up to n minus 1. And so our solution here is going to be a dynamic list, right? Data structure, where we're going to have all of the bells and whistles that we want. We want it to automatically grow and shrink without us having to worry about it. Right? We want to be able to do basic CRUD, add things, right? Remove things. Right? Remember CRUD: create, retrieve, update, and destroy. Those are the 4 basic things that you can do with a table. Same thing with a list data structure here. Create, in other words, put stuff in, add things. Retrieve, right? Not remove things, but retrieve things, right? Remove, that's the D of CRUD, right? Delete, right? The U is not that important because update, that's essentially taking something out and then changing it and then putting it back in. So we won't worry about that part, okay? But we want to do all of this without having to worry about the details. We want all the details to be encapsulated inside the data structure and not have to worry about them, right? Right? We want an abstraction, right? An interface that specifies how to use the list, not necessarily how it works, right? So we're going to want to keep this in mind as we're designing this data structure. Maybe some other functionality along the way if we want to. We can go ahead and, clear. There might be a way to clear the list. A way to shrink the list if its capacity is too much. In other words, you're wasting too much space. A way to copy one list to another, like a copy constructor. Find a particular element, search, right? Or insert at the beginning or something like that, right? So let's start at the basics, right? What my first iteration here is, my first demonstration, I should say, demonstration, is we're going to create an array-based list to hold integers, okay? And that's what I'm going to do over here. I'm going to call it, say, my integer list, array list. There we go. So I've got this new class. This new class is going to hold things, and it's going to use an array under the hood to hold these things. So my first step is, of course, to give this data structure here an array to work with. Should I make it public? Probably not. Private, and then let's go ahead and make an integer array, and that's what we had over here, right? And I will go ahead and make it big I integer array, ARR, all right, and I'll leave it like that. Right? I don't want to make this final because ultimately I am going to be changing this, and we'll see what that means here in a second. So this is a list. It holds things in an ordered manner. There's the first element, second element, third element, fourth element, etc. Right? And it's doing so using this array. Not just one, but an array. Okay? So now let's start thinking about the functionality that we want with this. First of all, what about a constructor? Let's make a constructor for this thing. Public, my integer list. Now, what do I need to do to set myself up in order to be able to add things to this array that's inside this list here? Can I add anything to that array right now? What value does this array have? No, nothing. In programming, nothing is what? Null, right? So what we need to do is we need to initialize this. This dot array is equal to a new integer array, but how big? 0? Can you hold anything in that? Nope. So let's go back over here to the demo. Okay. And what? Let's just go ahead and make it 10. Now, does that mean that there are 10 things in that array? No. Have we put anything into that array yet at all? No. It has a capacity of 10, right? I could put things in here from 0 up to index 9, okay? I could put things, non-contiguously or whatever I want to do. There's no interface here yet for the outside world to use this. Let me show you what I mean by that. What if I created my integer array list? Right? My list, right, is equal to new my integer array list. Right? There we go. My list dot. Can I do anything with it other than treat it like an object right now? No. Okay. So what I need to do is I need to add an interface over here. Well, what do you want to do with this list? Add stuff to it. Okay. So let's make a public, because of course we want the outside world to be able to add this stuff. Public add element. All right. I'll leave it like this for a second here. Okay. I want to be able to add an element. So what's the return value here? If you just put something in, do you expect anything back? No. So if you don't expect anything back from a function or a method, void? Okay. Add element. I need an element to add, right? What am I going to be adding? An integer. So let's go ahead and take an int x. Right? There's my element to add. Okay. Now where do I add it? Over here, I want to add, say, 10 to the list. If you just look, add element, sorry. There we go. And element. There we go. If you just had add element, where would you expect it to end up? Here are 5 things in there already. 10, 20, 30, 40, 50. And you want to add, say, 42 to the mix. Where do you want to add it? Next available spot. So in other words, to the end. Okay. That's perfectly that's a perfectly valid way of thinking about it. But where do we say where do we define that behavior? In good documentation, exactly. Right? So adds the given element x, code x, to the end of the list. So if we've got a list, we've got a beginning and we've got an end because it is ordered. There's the first element, second element, third element, etc. Right? And then there's the last element. If I've got 5 things in there already, 42 gets added to the last one. So now let's define this behavior. This dot array sub something is equal to x. What is that sub something? Well, how do I know how many elements are in that array? Do I have a way of knowing that? Say what? It's length. Okay, so I could use, say, array dot length, right? That'll tell me how big the array is, but remember, how big is the array? It's only ever going to be 10 for now, right? We're going to change that later. The array length dot is going to be 10. Now, is there an index 10? 0, 1, 2, 3, 4. What's the last index here? 9. Well, 9, right? And so 10 would end up being outside of the array. So what do I actually need? I need to know that there are 5 elements in there already, right? And where do I put it next? At index 5, right? Do you see a way of doing that with this current design? No. If you see a design flaw, does that mean you throw up your hands and say, okay, we're done, we're cooked, right? No, you change the design, right? What else should I be keeping track of up here? Private int size, right? All right. Then you tell me, what is the size initially? What is the size? It's 0, right? If you create an array, if you create a list and you don't put anything into it, how many things are in that list? 0. Okay. Now, what about this 10 up here? That 10 is not the size of the list. That 10 is the size of the array, which is inside the list. This is a capacity right here. I can hold up to 10 things here. How many things do I actually hold? I'm not holding anything yet. Right? All right. Now let's come back down here to add element. Now how would we end up implementing this? Where do I put it? Array, array, so what index do I put it at? Size. There we go. Why? If there are 5 things in there already, 10, 20, 30, 40, 50, where do I put 42? At index 0, 1, 2, 3, 4, 5. Right? And then return. Okay. Is that the end of the story? Update the size. Excellent. Why do I update the size? This dot size plus plus. Right. Well, if you had 5 things in there before and you add another one, how many do you have now? 6 things, right? So add that. Okay, let's come over here and test it. I'm going to go ahead and go into a loop for int I equals 10, I is less than or equal to 50, or actually let's go up to 110. Let's go with up to 100, I plus plus, right? And I will go mylist dot add element I. There we go. Let's run it. I added 10 things in there, except for what? Index 10 is out of down. This shouldn't happen. Say again, I can't hear. Oh, duh, thank you. 10. That's what I meant. We're going to overflow it here in a second. All right, great, it worked. But now, let me put 11 things into it instead of 99 things into it. Or 90 things, whatever it was. All right? Now, is this going to work? This is going to result in the exact same error as before. Why? It's full, right? I allocated only 10 spaces to hold elements, and then I added an 11th thing over here. So that's not the end of the story here. Right? That only works if you've got enough capacity to hold it. So what are we going to do? We're going to dynamically, automatically grow or shrink. If it becomes full, we need to grow it. If we want to later on, if it's only a small part of it is being used, maybe we want to shrink it down so that we're not wasting so much space. I want to take care of the first one though, so that it actually works. How do I increase the capacity of this list? Well, first of all, how do I know that it's full? Is equal to, well, 10, but let's not hard code 10 always. Because ultimately, if it's 10, now I'm going to say double the capacity, so now it's 20. And then add 10 more, so now the capacity is 30, right? I want it to grow. So if this dot size is equal to this dot array dot length. If it can hold 10 things, and 10 things are in there, then it is, the array is full, dot, dot, dot. So what do? We make a new array that's larger, right? And copy everything over. So make a new larger array, dot, dot, dot. How do I do that? Integer array, BRR, right, is equal to new integer of, well, how big should it be now? 20? Okay. This dot size, which is equal to this dot length, so you could use the length property if you wanted to instead. This dot size, and then how much more capacity do you want to add? We could go just 1, right? But then why did we start with 10? We wanted, we wanted something big enough to hold a few elements, right? So why go up just by 1 each time? I could go up by 10 each time. Or I could go up by 100 each time, or something. Or maybe, let's parameterize this, right? So block size, or something. Let's create a variable, and I don't want even the outside world to know about this variable. Private int final, in fact we can make it static, final int block size, and we'll just go ahead and be 10. Make it 10 for now. And we'll have an initial capacity of 10. Each time we need to increase the capacity, we'll increase the capacity by 10. That allows me to change this from 1 to 10 or to 100 with only one number here. Okay? I'll go ahead and keep it at 10 for now. Why did I make it static? Do I need a copy of 10 for every single list that I create? No. I just need one of these values that's associated with the class itself. Why did I make it final? Are you going to be changing this? Nope. Why did I make it private? I don't want anybody else to know about it, right? I want to encapsulate how this thing is working inside the class and close off the outside world from knowing about those details, right? Okay. So I've made it bigger. Now what? Make a new array, larger array. Do you want to lose that 10, 20, 30, 40, 50? Should we throw those out? Probably not. So copy over the elements, ... How do I copy elements from one array to the other array? For int I equals 0, I is less than array of length I plus plus. Copy over into BR. R. There we go. And at that point, are we done? I've got two arrays, right? R and BR. Which one belongs to the class? ARR. Right? So I've copied them over into this BR over here. What should I now do? This dot R is equal to BR instead. Right? Now, do I need to, say if this were a C programming language, I would need to free up the original array. Right? Well, I've lost a reference to it now, but I guess I could have done it before, right? Now that I've copied everything over, I can free this .arr and then make this .arr point to that new array over there. Do we need to worry about this step in Java? Nope. Why? Because we have automated garbage collection. When it sees that that old array is gone and nobody else has any reference to it anymore, it'll automatically clean it up. Right? Now down here, what we can do, we didn't change the size. All we did was increase the capacity. If the array is full, increase the capacity. And we've done that. Now that we've got a larger array, we can go ahead and copy over X, increment the size, and return. Let's see if it works now. Remember that we added 10 elements, and then we added this 11th element. And now it works. How do I know it works? Say what? There's no error, right? But how do I know that I've got 10, 20, 30, 40, 50, 60, all dot, 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 and then 42 in there? Well, one easy way that I could do that is what? System.out.println. Let's print my list. All right, let's print it out and see those 11 elements in there. Is that going to work? Oh, okay. So, encapsulation. If you want the behavior of printing something, a string representation of something, what should you be doing? A toString method. Let's do that so that we can actually look at it. Public string toString. Okay. All right, I want a string, so let's go ahead and make a string builder. SB is equal to new string builder. And the format that I'm going to use is I'm just going to go ahead and concatenate a square bracket, because that's how you represent arrays, sb.append, right? The square bracket, maybe some nice little space over here, right? And then for int I equals 0, I is less than, say, this.array.length, I plus plus. I will sb.append I plus, and then a comma. And then at the end, I will append a closing square bracket. There we go. And return sb.toString. This will be somewhat pretty, but it'll also be somewhat incorrect. Let's go ahead and try it. Is that correct? Nope. Okay, back to the drawing board over here. I am going up by tens, right? Yeah. 10, 20, 30, 40, 50, right? There's something else going on here. Oh, thank you. Duh. This dot array of I. There we go. Yes, I was just protein I. There. Now it's wrong in the way that I wanted it to be wrong. 10, 20, 30, all the way up to 142. But what about all these nulls? Is that actually part of the list? Nope, that's part of my capacity. Right? I can put stuff over there, but nothing has been defined over there. So what's the solution? Yeah, don't go up to array, just go up to size. That looks a lot better. There's a trailing Oxford comma there. Do we want to take care of it or not? No? Okay, how would you? -1 and then take care of the last one on the outside. Right. Size. There we go. Oops. Ignore that. I don't think I can ignore. Let's go ahead and run this again. Otherwise, no. All right. So clear. How do I clear it? There we go. All right. Ignore what I just did there. That was a code coverage tool, by the way, if you want to learn about that. It tells you if you have JUnit tests, for example, it can highlight all the code that was touched in a test or a suite of tests so that you can see, oh, well, there's this code right here without any green. I never tested that. Back to the drawing board. Let's write a test case for it. Right? Okay. That looks good. But you know what? Lots and lots of code there. 1, 2, 3, 4. 4 lines of code to copy an array. There must be a better way. This dot array is equal to arrays dot copy of this dot array. And why does it take this second argument over here, this x? All right? Let's read all about it. And unfortunately, I'm not going to be able to zoom in here. Okay. X. I'll leave it like that so that we can actually see it compile. Copies the specified array, truncating with nulls if necessary, so that the copy has the specified length. This thing over here is the new length. Right? It will automatically, if you want to create a copy of the original array, then you would just say this.array.length. Right? That'll copy it over. If you had 10 elements before, but you only want to copy the first 5, then you'd say only copy the first 5. If you had 10 elements before and you wanted to copy the first 15, it would copy the first 10, and then it would append it with a bunch of nulls, right? Which is exactly what we want. This dot array dot length plus, and what was it called? Block size? There we go. There. All is a one-liner. Don't reinvent the wheel. Use code that's already there. Okay. Well, I've been able to add things. I've been able to verify that those things are now in there, right? Of course, my other answer here would have been to, let's go ahead and set a breakpoint, right? And run the debugger. And when we do that, let's go ahead and highlight my list, expand it out. We've got a size of 11. Great. That's what I expect. And the array itself has elements 10, 20, 10, 20, 30, 40, 50, etc., all the way up to 42 at the end. Right? Proper debugging techniques instead of the poor man's debugger over here. Right? Okay. What's next? Retrieve things. Okay. I want to retrieve something in order to, I want to retrieve, say, the first element or the last element, or what's more general than that? An element at an index, okay. Right? If I implemented a get element at index, right, and then I gave it an int index, right, then that would enable me to get the first element. It would enable me to get the last element. It would enable me to get any element that I want. Right? So let's go ahead and make public void. Now, if you want to return something, you better be returning it, right? And what should I return? Integer or int, right? Since it's an integer array, I'll go ahead and keep it as an integer, big I integer. My design decision there has a consequence, though, right? somebody could add, or actually no, somebody could not add. Could somebody add null to this? Nope. I'll show you. MyList.addElement null. That is not going to compile. You cannot pass null when it's a little I integer. Now, if I change this to big I integer, in fact, I will, now this is perfectly fine. So do we want to allow nulls or not? If you don't want to allow nulls, you should better go back and change it, right? For now, I'll go ahead and leave it so because I do want to allow nulls, all right? Okay. I want to add an element. That element is, or get element at index, excuse me. All right. Return what? This dot array of index. And we're done. Right. Let's test it over here. Int foo is equal to mylist dot get element at index, say 0. Right. And then let's print foo. What should it print out? 10. Okay. Get element at index 100. What should it print out? Array index 100 out of bounds for length 20. Right. That's expected. If you were to do this with a regular list, built-in array list, or an array like I'm doing it right now, then of course that's going to result in an exception. Another one would be negative 10, right? You can't get that. Negative 10 is out of bounds. But for 20, where did that 20 come from? Did I put 20 things in there? How many things have I put in there so far? 10, 11, and then 12, because I added that null value there. 20, and also array index. I have a list. Do I have an array anywhere here? Nope. This is leaked a little bit of my abstraction. This is called, again, a leaky abstraction. I've leaked information about the workings of my data structure to the outside world. Right? When you're driving a car and a problem occurs, what happens? Check engine light comes on. Does it tell you that the carburetor is, I don't know anything about cars, so does it tell you that the carburetor is out of oil? No, it just tells you, look, there's something wrong, right? We're not going to tell you what it is because you're not a mechanic. We're not going to assume that you're a mechanic. We're not going to give you 50 million, reasons why this went wrong. Something went wrong, period. Right? Think about this from think about another situation where everybody's experienced the blue screen of death, right? With Windows. What happens when Windows crashes? Blue screen of death, and then now is the average user supposed to go in and say, oh, there's the memory address. There was a fault at that memory address. I need to hop on and tell Microsoft about that they had a null pointer, dereferencing a null pointer on line 58, right? Grandma's not going to be doing that, right? So we don't want to leak abstractions out of our class. Let's go in and let's do some basic error handling here, right? If the index is invalid, if the index is negative, or what's the other, on the other end, when is my index invalid? Greater than or equal to size, right? Because if there are 10 things in there, can you get the element at index 10? Nope. You can get the element at index 9, but not beyond that. All right. If that happens, what should we do? Let's throw an exception, because that's how you do error handling in Java. A new runtime exception. But instead of giving them this mysterious leaked information here that actually I'm using an array, and also its capacity right now is 20, right? 20, I only put 12 things in there, right? That doesn't make any sense, right? Let's go ahead and give them a more sensible message. Now, we don't have a technically incompetent person reading these messages because they are exception messages. but we should be a little bit more, you know, descriptive for the actual list here. Right? So I'll just say index out of range. Right? List is of list currently holds, and I'll give them a message here. This dot size elements. You can be as helpful or unhelpful as you want. Right? And now let's go ahead and run this again, and I get that information now instead. And it's a runtime exception. Right? If you want to, you can make your own list exception of some sort if you want to, and then be more specific about it. Right? I'm just going to go ahead and leave it as a runtime exception with this more sensible error message here. It currently holds 12 elements. You can't give me that index. In fact, we could tell them what index they tried. Right? Plus plus, index, and then index 100 or -1, whatever it was, 10 is out of range. Right? We could put in the valid ranges if we want to. Right? We can be as descriptive as we want in our error messages here. Right? Okay, that seems a lot better. Right? No more leaky abstractions out of that. Assuming that we didn't throw this runtime exception, we're simply returning the element at that index. Are we changing the array? No, we're just taking we're just retrieving something. If we were to remove something, what would it look like? So let's go ahead and go with a public void for now. Remove element at index. Int index. Okay. What should I do here? Error checking again. In fact, it's going to be a cut and paste. Right? And maybe I can put that into another function that checks to see if the bounds are correct. Right? So I'm not repeating that all over. Right? I'll go ahead and leave it like this, though. Right? Otherwise, remove array sub index. How? I did set up my iPad for the day. So, smaller example. 10, 20, 30, 40, 50. I want to remove 30. Is it enough to simply just say, okay, 30 is gone? Because now you've got a gap, right? So, how do I take care of that gap? Okay, shift it all down, right? Move this one so that it's over here, 40. And now that 40 is gone, do what now? Move 50 over. Do I need to remove 50? I could, in effect. How? If it was of size 5 before, what size does it become now? Or size 5 before it becomes now 4, right? So, does it matter if I leave that in there or not? Who cares? So, I'm going to go ahead and remove an element by simply shifting everything out after it all the way down. Okay? Help me out. Right. For int I equals 0, I is less than this dot size I plus plus. Right. Shift I plus 1 down to I, dot, dot, dot. Do I want to start at 0, though? No, where do I want to start? At the index. The indices here were 0, 1, 2, 3, 4. So if you want to remove the element at index 2, where do I start? 2, and then take I plus 1 and move it down to I, right? More generally. Okay? So start at index. We've already checked for the inbound, outbound, etc., right? So we'll start at index. We'll go up to something, who knows. We'll come back to that. I'll shift I plus 1 down to I. So this dot array of I is equal to this dot array sub I plus 1. There we go. Now, because I'm always looking ahead, what do I go down to? Or go up to, I guess. Second to last one, which is where? This dot array dot length. Nope. Remember that this is going to have a capacity, so there could be stuff out here, right? And I don't want to be mucking with that at all. Right? So size, I think I heard size, this dot size, certainly, and then -1. Let's see if it works. Right. So remove element at index. My list dot remove element at index, and let's just remove something in the middle, say 5. Right. What should it look like then? Get rid of this because we tested it already. Right. 10, 20, 30, 40, 50, 60, 70, 80, 90. Oh, I guess I should print it out again, right? There we go. So index 5 is going to be which one? 0, 1, 2, 3, 4, 5. I'm ultimately removing 60, right? So I should have 10 through 50, and then 70, and the rest of them should be shifted down. Let's see if it worked. Right. Well, 60 is definitely gone. 70, 80, 90, 100, 0, 42, 42. What did I not do? Say, change the size. This dot size minus minus, because you just removed an element. Right? Okay, good. It looks like it works to me. What else should I be testing here, though? If I were to write a test suite in JUnit, what else would you want to test? Maybe some corner cases, like, for example, does it work when the index is 0? Remove 10 instead. Yeah, it works. You'll want to test your error conditions. Remove index thing at -11. You expect an exception to be thrown. What's another corner case? At the end. Is 12 the end here? Remember, it was of size 12. And is there an index at 12? Nope. Okay. So the last one would actually be at 11. We're removing that 42. Let's see if that works. It works. All right. So when I added something in, I had to make sure that there was room enough for it. When I'm removing something, what's the opposite? Maybe if I have too much wastage, if I've grown my list to 1,000,000 elements, right, and I'm only using the first 10, does it make sense to keep all of that in memory? Maybe not. So maybe to do, consider a shrink operation, right? Grow or shrink operation, right? And I'll leave that as a to-do there, okay? Anything else that we would want to add to this function to make it a little bit more functional, right? A little bit more flexible or usable? If you remove something, so here's 30, take it out. Still got it in my fingers here. Just throw it away? Oh, okay. What if I expect something to be returned from it? Int x is equal to this, right? And then I can print out x, I can print out the list, and I can print out x to see that you remove this element, and here you go, here it is. If you end up ignoring it, for example, you don't capture it into a variable value, that's your business, right? Your choice. You can do one or the other, but the way that I have it designed right now, I'm not giving you a choice. So let's come back over here and give somebody a choice. Integer. Okay. Remove element at index. What do we need to do? We need to return the removed element. ... Okay. Do I still have it at that point? Nope, I overwrote it by shifting stuff down. Whatever was in there that I got rid of, I was already overwritten. So what should I have done before I started that shift down process? Kept it, right? Integer x is equal to this dot array of index. Right? You're saving it off, and then down here you can return it. Okay. Remember that we're removing the last element here, so it's going to be 42, and we end up printing 42. Now it's a little bit more versatile, right? We increased our interface. We made the abstraction better because we're not locking you into one way of using this list. If you want the returned element or you just want to remove it and ignore it, go ahead. You can use it one way or you can use it another way. How do I know that? By writing good documentation. Removes and returns the given element, or the element at the given index. Right, period. Do we say that by the way, we shift things down so that there's no gap. Oh, and by the way, future tense here, we actually implemented a shrink method. So, and also we decremented the size. Do we have to worry about any of that stuff over here? No, because we have good abstraction. Right? All of that is opaque to us. We don't have to worry about any of those small level details. Okay? So I've got a way to add things, a way to retrieve things, a way to remove things. Anything else that we want to add before we go on? Well, add element only ever adds at the end of the array. What is maybe a little bit more versatile way of using this? What? Add it at a certain index. Public void add element to at index. Right? So integer x is the element that we're going to add, and int index. Why did I choose not to do an integer index? Can an index ever be null? No. So I'm forcing you to give me a valid index, well, at least a valid number here, right? Okay. Same thing as before. If we're going to add something but we're already at capacity, then we need to increase the capacity. Otherwise, this dot array sub index is equal to x, and return. Except that also this dot size plus plus. Is that going to work? Oh, we should definitely do some index checking here now that we have an index. All right. So add element at index here. But what in this instance is a valid index? Let's come over here and look at an example. Right? So if I've got, say, 10, 20, 30, and 40, but I still have some more capacity over here. Right? Dot, dot, dot. The current size is 4. Right? There are 4 elements in there. Does it make sense to add something at index 0? Yeah. Right? Does it make sense to add something at index 1? Yeah. Right? What does it look like if we add if we add 42 at index 0? 42, 10, 20, 30, dot, dot, dot. Right. What does it look like if we add it at index 1? 10, 42, 20, dot, dot, dot. Right. Does it make sense to add here? Yes. Here? Yes. Right? In which case we would have 10, 20, 30, 42, and then 40. Does it make sense to add something right here? That's a what? That's what the other function does, right? And we allow that, right? So a valid index might be 0, 1, 2, 3, and 4 here. So let's change our condition here that if it is strictly greater than size. Again, if the size is 4, 0, 1, 2, 3, 4 is valid. That just means adding it to the end of the list, right? Or at the end of the end of the list. Right? I'll keep the same error message there though. Okay. All right. If we don't have enough room, increase the size. Put it there. Increase the increase the capacity. Excuse me, and then increase the size. Is that going to work? Let's find out. My list. Dot add element at index, and let's add it to the front here, and I'll add element, or say 101, and then at index 0. So I would expect this now to be we've removed 42 here at the end, so it should be 101, 10, 20, 30, 40, 50, etc. if we printed this out. Is that what I'm going to get? What happened to my 10? So I didn't implement a remove or add element and index, did I? I implemented a replace element at index, If that's what you want to do, go ahead. That's not what I wanted to do, though. So what do I need to do to make sure I'm not overwriting whatever you're doing, or whatever you have at index already? Yep, shift. Right? Shift things. So shift things up down here. When we remove something, we shifted it all down. Here, I'm just doing the opposite. Shift it all up. Right? So shift things up to make room at index. ... How am I going to do that? Let's visualize it over here. Oops, sorry. There we go. Let's go 10, 20, 30, 40, and then there's still capacity over here. Right, there we go. How do I shift things? Can I want to insert 42 here. Can I go ahead and just copy 10 over here? Now 10 is there? No. Okay, well, I had to move 20 first, right? Okay, so I'll move 20 over here. Okay. Does it seem like going left to right is the correct solution here? No. Back, 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 back. All right. So, what should I do first? Move 40. 40 over here. And then it doesn't matter if I delete it or not. I'll just move 30 over here. Doesn't matter if I delete it or not. 30 or 20 comes over here. Right? And finally 10 goes in here. And now I can go ahead and put a 42 in there. How did I do that? Remember, the size originally was 4. So where am I going to start my index? If I want to shift this thing over here. Size minus 1, right? Because this is 0, 1, 2, 3. I want to copy I to I plus 1. Right? So start at I being size minus 1. In other words, at 3, then copy it over 4. And then go down by 1s. I minus minus. But when do I stop? I'm writing my for loop here. I copy 10 over here. I stop when I hit that, including that last index there of wherever you're trying to insert it. So that tells me that I need to write a loop that looks something like this. For int I, starting where again? Size minus 1. And I'm going to go down, I minus minus. And I will copy this dot array of I to our plus 1 to this dot array of I. There we go. Again, I'm copying the ith value into I plus 1. I'm putting the ith value into I plus 1. Now, what do I go up to? Or down to, I guess, because I'm working right to left. While I is still greater than or equal to the index at which you want to insert it. Okay? And then that makes room for it down here. Let's see if that worked. Remember, it should preserve 10. It should be 101, 10, 20, 30, all the way up there. There we go. Good? Remember that 42 is out of the game already here. So it should go all the way up to null, just like up here. Right. Okay. Lots of repeated code here. Lots of repeated code, right? In fact, this is repeated. This is repeated. So which one of these functions is more general? And which one's more specific? Which one could I have one of them call the other? Would it make sense for add element and index to call add element at end? That's more descriptive now. Or would it make more sense for add element at end to call add element at index? What would it look like? This dot add element at index. You want to add x to where? This dot size. one liner. Right? In fact, that gives me cause to actually rename this at end, because what if you want to do the opposite? What if you wanted to add element at, what's the opposite of end? Start, beginning. We call these tails and heads. Why? You got a head, you got a tail, right? I could call it heads and tails here. I'll go ahead and call it start. But instead of calling this dot size, what would I pass? 0. Wow, right? All I had to do was write this one general function, and I now have two other functions, methods, that use that function, and I've got a very, very flexible interface that I'm publishing to the world here. Okay? Add element at end. Oops. At end. There we go. And it still works. Okay. What else do we want in this? Anything? I've got a way to put stuff in. I've got a way to take stuff out. I've got a way to remove stuff, right? Maybe a way to clear the list. Right? Remove everything all at once. A way to shrink the list if the capacity is too large. A way to add multiple elements at the same time. Here are these 5 things. Here's this array. Add them all, right? Here's this other list. Append that list to the end of your list. Right? A way to copy one list to into another, a copy constructor. Find a particular element, right? Insert at the beginning, right? Which one do you want to do? What about find element? Public Boolean contains element. Integer x. I bet it should have been documented throughout this entire thing, but let me go ahead and describe what I want to do here. Returns code true if this list contains the given element x. False otherwise. And I'll let you write the HTML to code that up. Right. How do I do it? For int I equals 0, I is less than this dot size, I plus plus. Right. If this dot array of I is equal to the thing that you were searching for, then return true. Otherwise, return false. There's a name for this, algorithm that we just wrote. What is it called? Start at the beginning. This isn't it. This isn't it. This isn't it. You get all the way to the end. I didn't find it. Right? I'm not sorting yet. I am searching. What kind of a search am I doing here? I'm not cutting it in half each time. This is linear search, right? So if you want to, you can document that. This method performs a linear search algorithm. Right? Sometimes it gets lucky and finds it at the first index. Sometimes it gets unlucky and doesn't find it at all, making n comparisons if you've got n elements in there. Right? That's why we called it linear. Right? In average, it's going to take n divided by 2 comparisons to find what you're looking for. That's a preview of algorithm analysis that we'll get into deeper after this. Okay? All right. What if you wanted to do a binary search? Good question, right? What if I wanted a public Boolean more efficient contains element integer x? Right? What would I have to do? It's going to perform a binary search now. Performs a binary search on the list to find x, ... What would I have to do first? Do we remember binary search? If not, we need to review a little bit. Let's go with 10, 20, 30, 40, 50. Right? I want to search for 45. Okay. What do I do first? I look in the middle. Is that the thing that I'm looking for? Nope. The thing that I'm looking for is larger. So since it's sorted here in ascending order, where do I search for it? Above, in the right half of the list. Immediately saying that I don't need to look at the left half of this list, at the lower half of this list at all. Right? All right. Well, treating that as my new list. Right? Look at the middle element. Is that the thing that you're looking for? Nope. So you would end up. Let's go ahead and change this to 35. Right? Because I wanted to go the other way. Right? And now you're looking at this list right here, which is of course empty. And so you'd say, okay, 35 unsuccessful search. What does it require to run binary search on this? It needs to be sorted. Okay. So this dot array dot sort. Is that how I sort an array? No, there's no sort method on it. Arrays don't have functions, right? Arrays don't have methods. Arrays dot sort though does. This dot array. This dot array. Right? And then I can do a binary search. Arrays dot binary search for this dot array and x. Now remember, what does binary search return? It returns an integer, the index of the search key if it's contained in the array. Otherwise, it returns a negative value to say that that element does not exist. I need to translate that into a Boolean value here. So int index is equal to this. Right? If the index is less than 0, that means it does not exist. So I should return what? False. Right? Else return true. Okay? There. Now, does that seem right? Performs a binary search on the list to find x. Let's go ahead and repeat our documentation up here. Returns true if this list contains the element x, false otherwise. This method performs a binary search algorithm. What else does it do, though, that I'm not telling you? Let's find out. Well, yeah, okay. This is good enough. Let me take out these two parts here. All right. Print it out. Let's take out this part too. Add that element. I also wanted to add 42. My list dot add element at end 42. There we go. We'll print it out, and then we will ask it for if my list dot contains element, say, I don't know, 80. Right? Boolean foo is equal to this. Print it out. System.out.println. Should it print true or false? True. Okay. But now let's also print out the list itself. So it'll print out true, but uh-oh. Oh, sorry. It contains, what was it called? What stupid name did I get? More efficient contains element. There we go. There. Oops. Ooh. Ah, good question. What happened? Yep. Can you compare no? Nope. Okay. So back to the drawing board. All right. Well, let's just go ahead and make it so that it passes for now. All right. I'll go up to 80 and then add those other elements so that I never grow my array. There we go. All right. That's just my quick jerry rig, right? Is that what they call it? Jerry or, yeah, jerry rig. I just jerry rigged this so that it would work, right? So true, it does contain 80. It's right there, I see it. But is it the same list anymore? Here's my list from before, and I simply asked a question, a true or false question. Right? Does it contain 80? And then it goes and mucks with my list. Right? It changes the how my list worked. Right? Does that sound right? No. That's kind of a leaky abstraction in that it's doing something other than what I intended it to. I just asked a question. Does it contain X or not? Right? Well, I'm going to go ahead and muck with your list and change it, and then I'll tell you true or false. Right? It shouldn't be doing that, should it? So one solution would be to don't sort it, instead sort a copy. Right? This dot, copies of create another copy, integer. I don't even want to do this because this is not the solution. Copy of is equal to arrays dot copy of this dot array, and the same thing, right? This dot size. Copy that over, sort the copy, then search the copy. There. Now from the outside world, it looks like it's much better. I didn't change the list. I changed a copy of the list. Right? But does that still seem that doesn't seem right? Right? Does anything about this suggest that this is an ordered list, right? There is a first element, second element, third element. When we say ordering, that means that they're ordinals: first, second, third, fourth. Right? But is this a sorted list? Doesn't seem like it to me, right? So let's rethink this. What if I did want a sorted list? What would it look like? Get rid of all that. Get rid of this. Let's go ahead and I'm going to go ahead and create a copy here. Right. My sorted integer list. There we go. My sorted integer list. There we go. All right. Let's think about this if it's already sorted. Right? Now, when I create one, right, it's going to be empty. Do we have any concerns here yet? Nope. Adds an element to the end. Right. Okay. Should this even be here? If I have, say, come on, register. There we go. 10. 20, 30, 40, and I want to add 5 to the end of the list. Should I be able to do that? That doesn't seem right. That's not a sorted list, right? Allowing arbitrary access to this list, right? Well, it sounds like you want a regular old list. Go shopping over there. If this is a sorted list, you shouldn't be able to add something to the end. You shouldn't be able to arbitrarily add something to the start. Should you be able to add something arbitrary to, well, here, let's get rid of this for now, right? Well, no, I'll keep that, right? That's fine. But should you be able to add something to an arbitrary index either? Put 5 right in the middle of 10, 20, 30, 40, 50. Nah. What if we had a generic add element X? What would it look like in order to maintain the ordering? In other words, if I want to add 5, I'm going to allow you to add 5. Where do I add 5 to? Where it needs to belong, where it needs to be, 5 right in the front. What if I want to add, say, 35? Add 35. Where does it need to be? Right here. Right. What if I wanted to add 42? Where does it need to be? At the end. Right. I'm the list. I'll decide where it goes, right? Because I'm a sorted list now, right? I am a sorted integer list. You give me your integer, and I'll put it where it needs to be. Okay? Do we have index issues anymore? Nope. Do we have capacity issues? Yes. Right? Because if it's full, there are 10 elements there, and you want to add 42, I'm not going to tell you where I'm going to add it because I'll take care of those details, right? I still need to increase the capacity. Right? So I shift things up to make room for it at the index where it belongs. Okay. How do I find the index where it belongs? Write some code to do it. Right? So find the index at which the element X belongs. Dot, dot, dot. Okay. for int I is less than, or is I is 0, I is less than this dot size, I plus plus, right? I'm going to go ahead and put, say, int index here, right? Right. What's my condition here for updating? Where do I start my index and where do I put it, right? I'll start it at 0 here. Should it go at 0 or not? If this dot array of I is less than the thing that you want to put in, right, then does it belong at I? Nope. So 10, 20, 30, 40, 50. You want to add 60, right? 60 and 10. Does it belong there? Nope. Does it belong there? 60 now. Nope, 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 nope. Where does it belong? Right here. Right? So if x, which is my finger right here, 60, is greater than this, I move on. Move on, move on, move on until you get to the end. So index plus plus. Right? Now, what if I have got 10, 20, 30, 40, 50, and I've got 5 here now? Right? Is 5 greater than 10? Nope. So what's my index when I break out of this for loop? 0, and that's where it needs to be. Right? Okay. That looks really good. In fact, I could have taken the code that I had before, and I knew that it worked, right? Add element at index. I don't want to have to rewrite this and retest this. Let's go ahead and keep it. But should I make it public? No. Make it. I want to use it. I'm the list. I want to use this now. So instead of taking care of all of this stuff now, I can simply say this dot add element at index. I'll add x to that index. Find the index at which it belongs, and then take care of it. Right? Now there is some leaky abstraction here, but this will never happen now because we are taking care of all the details. But add element at index. We don't need this now. All we need to do is find the index at which it belongs and then add it. Let's come back over here and change my sorted integer array. Change it to that, change it to that. I can no longer add an element at index at the end, right? We only have a few minutes here, but let me go ahead and show you how to maybe test this rigorously. Random r is equal to new random. What do you think that is? A random, well, it's a random generator of anything you want. Random strings, random numbers, random floats, whatever you want. Right? So I'll go ahead and go with 0, I is less than 10, I plus plus. I'm going to add 10 random things into this. R dot next int. There we go. And print it out. I don't know what's going to go in there. In fact, if I run this multiple times, I'll get different random numbers each and every single time. But what do I expect on line 15? That it's going to print out sorted every single time. Right? That looks kind of ugly. So let me go ahead and make it so that it's between 0 and 99. I don't want to look at those numbers. Right? Is that sorted? Looks like it to me. Do it again. Do it again. Oh, come on. If I do it really quick, I'll probably get a repeat. Because the seeding is based on time. No, I'm not going to be that lucky anymore. Ooh, duplicates. Does it handle the duplicates? Did you see any duplicates? We can make it small so that we're almost guaranteed to get a duplicate now. It handles those duplicates. Right? More testing. 1,000 elements. Looks good to me. Zeros, ones, twos, threes, dot, 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 etc. Right. Now, is there anything else wrong with this? And again, we made this private. It's okay to have things that break the semantics of your class. It's not okay to let somebody on the outside world break them through a public method. Making this private is perfectly fine. Add element is fine. Get element at index. Yeah, you're not changing it. There's no way that you can screw up the ordering of that. Remove element at index. Yeah. Right. 10, 20, 30, 40, 50. It's in order. 30, take 30 out, shift everything down. It's still in order. Right? ToString. No changes there. So, seems like there's a lot of repeated code here, though. In fact, let me go ahead and compare these with each other. Compare with each other. So the question I'll leave you with for next time is, when we've got repeated code between two classes, what is that suggesting? Not screaming out in this case, but what is that suggesting that you might want to do with those two classes? One's a list, one's a sorted list. Do maybe inheritance somehow. Think about the inheritance in this case, though. Is a list a sorted list? Is a sorted list a list? Conceptually. We'll explore that on Tuesday. All right, we'll implement that inheritance and see if it works for us. Okay. All right, have a good weekend.